Hello everyone, I am Yashvardhan Marda. I'll be explaining simple physics to you all. Let us start with the first topic, laws of motion. Some of the examples of activities that involve laws of motion can be, suppose we can say the first example is catching of a ball. So now how do we catch a ball? There is this person standing right here. Let us suppose a ball comes straight towards him into his hands, and let us suppose that the batsman who has hit the ball has hit it very hard. So now, and it's in a projectile motion, suppose like it's going in this path. He has hit it very high and hard. So now how can we reduce the force that is being applied by the ball on our hands? So there is this formula in physics which is known as the impulse is equal to force into time. So from here we can say that force is equal to impulse divided by the time taken. So here the force is the force applied by the ball on our hands, and here the time is the time taken to catch the ball. So we can see that if we make this quantity in the denominator less, or rather more, if we make the quantity in the denominator more, then the ratio will become really small, and so the force will become small. So that means if we increase the time taken to catch the ball, then by increasing this, the ratio will be small, and since this is equated with the ratio, force is equated with the ratio, the force will also become small. So the force exerted by the ball on our hands will be very small. So this is how we can prevent injuries on our hand. So this is one example of catching of a ball. There are three laws of motion as explained by Isaac Newton. Let us move on to the first law of motion. First law of motion, or the law of inertia, it states that every object in the universe remains in a state of rest or uniform motion unless acted upon by an external agency. Now this external agency is what we call as force. And this right here. External agency is the force applied. I'll write down the law also here. Every object in the universe remains in a state of rest or uniform motion unless acted upon by an external agency, and this external agency is nothing but the force applied. So now this is just a theoretical meaning of the law. Let us just understand. Let us take a case study and understand what it actually means. Let us say this is the Earth and this is the Mars. Let us suppose we launch a rocket from the Earth to the Mars. let us say the rocket, when we launch it, it revolves in a circular orbit around the Earth, and then it slingshots towards Mars. So let us say at any point P, this rocket is right here. It is at point P. So when it was inside the Earth, when it was launching towards its atmosphere, when it was at, let's say, point A, there were a lot of external forces that were being applied on this rocket. Suppose we can say air resistance was being applied on this rocket. So here, if we stop the ignition of the rocket, then the rocket will fall back down because of the external forces applied. Here at this point, I write it, at point A, there is some external force applied, let's say F. And because of this external force applied, if we stop the ignition of the rocket, that means the fire coming out of it, then the rocket will fall back down. That means it will not obey the first law of motion, obviously, because there is external force applied, and the law says that no external force should be applied. On the other hand, when it is in space, just free space, no planets or any gravitational pull of any celestial body, therefore at point P, the external force applied, I write it here actually, at point P, the external force applied is 0 newtons. That means if there is no external force applied, this will obey this situation right here, it will obey the first law of motion. Now, if what happens is that to conserve fuel, scientists close the ignition of the rocket, or rather they stop the ignition of the rocket. This has stopped right here, so that they conserve their fuel and reach safe. The rocket conserves its fuel and reach safely towards Mars. So now, if we stop its ignition, it will move. Let's say it was initially moving with a velocity. It was initially moving when this rocket was here. It was initially moving with a velocity v. Now if we stop the ignition, the rocket will continue to move with the same velocity v, or the acceleration we can say a, because there is no external force applied. So if there is no external force applied, it continues to remain, I'm sorry, there will be no acceleration actually, because it continues to remain in its state of uniform motion. Uniform motion is, that means it continues to move with the same velocity. It does not change its velocity. The velocity remains constant, and therefore by closing the ignition and using the first law of motion, the rocket can reach very safely towards Mars. This is one practical application of the first law of motion. So now law of motion is also known as the law of inertia. And what is inertia? Inertia, it is the property of a body by the virtue of which it cannot change by itself its state of rest or uniform motion. So now inertia is proportional to the mass of the body. So now we can say that let's say there are two boys right here. Let's say this boy is kicking a stone which is of mass, let's say this is a stone of mass capital M, and this boy is kicking a football which is of mass small m, and the situation is that capital M is greater than small m. So now since capital M is greater than small m, that means that the inertia will be greater in this case, because it is directly proportional to the mass of the body. So that means this boy right here will have to apply a greater force to move the stone than the boy which has to apply the force to move this football. So the force applied, let's say this boy is A and this boy is B. Force applied by boy A will be greater than force applied by B. This is because inertia of A is greater than the inertia of B. So this is the law of inertia again, the first law of motion only. So now there are three types of inertia: inertia of rest, inertia of direction, and inertia of motion. Let's move on to the first type of inertia. Now what is inertia of rest? It is the tendency of a body to remain in its position of rest, and that is the inertia of rest. Let us understand this by an example. Let us say that there is a bus and this it has just one passenger inside it, and this bus, this is the initial case. This bus is initially at rest, that means the velocity is 0. At rest means the passenger is also at rest. Now suddenly, let's say, this is the first case. Let's say in the second case, the bus suddenly begins to move with the velocity v. Now what will happen is that our legs are actually attached to the ground. So they will move with the ground. The ground, by ground I mean the floor of the bus. So the legs will also move with the velocity v, and our upper body is not attached. So it will experience a force backwards. It will experience a jerk basically, and that is what happens when we sit in a bus and it suddenly starts to move. We experience a force backwards, and it is not because it is because actually due to the inertia of rest only, because it was initially at rest and it wants to remain at rest. So half of our body which is attached, that means the legs, will move with the velocity v of the bus, and half of our body which is not attached will want to remain at rest. Therefore we experience a jerk backwards, and this is a very classic example of the inertia of rest. Inertia of motion, it is the tendency of a body to remain in its state of uniform motion, and let us understand this again using an example. Let us say this is the bus again, one passenger sitting inside it. This is the initial case, and this time initially the bus is moving with the velocity v, so that means the passenger is also moving with the bus with the velocity v, and let us say in the final case the bus suddenly stops. The bus stops, that means v is equal to 0 meter per second. That means this is at rest. I mean it suddenly stops. So what will happen is that we experience a jerk forward. Now why does that happen? It's because since the bus is not moving, that means the legs attached to it are also not moving, but the upper part of our body is independent of the legs attached. That means the upper part of the body wants to continue to move with that velocity v. That means it wants to obey the inertia of motion. So when it wants to obey the inertia of motion, our body, half of our body will move forward and half, that means with the same velocity v, and it wants to move, and the legs right here, they will stop because the bus has stopped and the legs are attached to the floor of the bus. So therefore we experience a jerk forward in this case. In inertia of rest, we experience the jerk backwards, and in inertia of motion, we experience a jerk forward. inertia of direction, what does it say? It is again the inability of a body to change by itself its direction of motion. That means it wants to continue to remain in the direction of the motion. And let us understand this again by an example. Let us say this is a straight road and then it curves at this point. So now what will happen is that let us say there is this car which is mass, and we can say, though the mass is not what we are looking for here. Let us say this is a car and it moves with a velocity v, and let us just remove the mass. There is a passenger sitting inside the car, and when this car comes at this point and takes this turn, what will happen is that basically the passenger wants to remain in this direction of motion, wants to remain in the rectilinear motion. Rectilinear motion is the straight line motion. We can assume this is a straight road, and it wants to remain in its rectilinear motion, but however the car negotiates a curve to the left hand side. So what will happen is that when the car is negotiating a turn here and the passenger, it wants to remain in this position, in the rectilinear motion, we will experience a jerk on the opposite side. That means if the car is negotiating a curve on the left hand side, we will experience a jerk on the right hand side. As we can see also when we go on the road and there's a sharp curve coming ahead, if the curve is directed towards the left hand side, we experience a jerk on the right hand side. Well, on the other hand, if the curve is directed towards the right hand side, we experience a jerk towards the left hand side. I hope that this is clear. Let us move on to the second law of motion. Many people confuse the second law of motion with F is equal to ma. However, this is correct, but again it is actually incomplete. So let us understand the complete meaning of the second law of motion. So now the second law of motion states that the rate of change of linear momentum of a body is directly proportional to the applied force, and the change, we can say, takes place in the direction of the force applied. To understand the second law of motion, we need to understand what is momentum. So basically, momentum is a vector quantity. It is denoted by symbol P. For those of you who don't know what is a vector quantity, it is a quantity which has both magnitude and direction, and it obeys the second law. It obeys the vector law of addition. So momentum is equal to the product of a body's mass and its velocity. Velocity is also a vector quantity, and its units, momentum's SI unit is mass is kg and velocity is meter per second, so its SI unit is kg meter per second. So now we have understood what momentum means. Basically we are not concerned about the SI unit, we are just mainly concerned about its formula here. This is the formula of momentum, mass into velocity. And now the second law of motion means that the rate of change of linear momentum and linear momentum, I am just assuming this momentum as linear. I will write it here also. This is linear only, it's not angular or something. This is linear momentum. So the rate of change of linear momentum, whenever I say rate, that means we need to divide the quantity by the time. So that means P by T. This is the rate of change of linear momentum. Now this happens, we need to put a differential operator here, that is d by dt. So mainly this right here, this is a differential operator, and this means that it happens in a very small time t. So So now dp by dt, this is the rate of change of linear momentum, and this is directly proportional to the force applied. This is exactly what is the second law of motion means. Now, if we solve this further, we get that the force, to remove the proportionality sign, we need to put a constant which comes out to be k, and its value is its value scientifically has been found to be 1. So I'm not writing that because 1 into something is just this only. So F is equal to dp by dt, and we know that P is equal to mass into velocity. So that means force is equal to d by dt, and this is mass into velocity. Now there are two cases here. What happens is that in these two cases, if we consider the mass as constant, we can't put, so suppose if we consider the mass as constant of a body, which usually is, because the mass does not change, so we can bring the mass outside, because differentiation happens it will not happen of a constant. So we can bring the mass outside. That means F is equal to m dv by dt. This is if mass is constant. And this further is what we call as F is equal to ma. Now I'll explain how this comes out to be a. Acceleration is actually rate of change of velocity. So I explained earlier also. Acceleration is, let's say, rate of change of velocity, and this writing v by t here, let's say del v by del t. V by t is the rate of change of velocity, and we put d as the differential operator. That means it happens for a very small time interval, at a very small time interval. So acceleration is dv by dt. Acceleration is also a vector quantity. So we can replace dv by dt with the letter a, which represents acceleration. So from here we get that F is equal to ma, and the second case is, this is the first case of F is equal to dmv by dt. I'll write it again here. So the first case comes out to be F is equal to ma. And now the second case is when the velocity is constant and the mass is actually variable. Now this usually it does not happen, but I mean it can happen, but again we'll not get into that because it becomes quite complex. So the mass can also change, and let's say the velocity is constant. So again, if something is constant, we bring it out of the differential of the derivative. So from here we get that, in the second case we get that F is equal to, we bring the velocity out since it's a constant and the mass is changing, so the differentiation will be of the mass with respect to time. This is the second meaning of the law of motion. So now I hope you understand why I said that there are two cases of the laws of motion, and why many people confuse it with just F is equal to ma. It's also F is equal to v dm by dt. So this is the first case and this is the second case. Both are correct and both are valid in all cases. Not in all cases. Again, this is valid when the velocity is a constant. So the third law of motion states that every action has an equal and opposite reaction. Now again, we can understand this statement using some examples. So now let us move on to some, there are two examples of this through which we can understand the third law of motion. let's say this is a table and a book is kept on the table. One second, my drawing is not so good. This book is kept on a table. So now we have never wondered why the book, it does not, break the table or move upwards. It when we keep it on a table, it remains at that spot. So now what happens is that, let's say the book has a mass m, so a force will be acting downwards, which is the force of gravity, which is m into g. G is the acceleration due to gravity, and this force is exerted by the earth on this book. So the earth exerts on a force on this book, which is equal to mg, and the table also exerts a force on this book that is equal to r. So what happens is that r is equal to mg. That is why, since these two are equal, the book stays in its place and it does not, break into the table or move upwards. Now, one more thing we can notice here is that both these forces are in fact, one force is acting by the, one force is due to the earth on the book, and one force is due to the table on the book. So there are two forces which are involved here, and since these two forces are equal, therefore the book is always kept on a table. So these are action-reaction forces. R is the normal reaction, and again it's exerted by the the table. It's exerted by the table on the book. The second example of the third law of motion is the case of walking. Let's say this point is our foot, and so now when we walk, we notice that we exert a force right here, like this. You can, if you don't believe me, then you can just go around and walk, and you will notice that your legs will exert a force in this direction. This will be the force applied by your legs, and opposite to the force will be another force applied by the ground on your legs, which is again the normal reaction, R. Let us say we draw a line. Let us say the normal, this is the floor, by the way. This is the floor. So the normal reaction is a force which is exerted by the floor on your foot, and this makes an angle. The R makes an angle theta with the floor. So now this quantity right here will be R cos theta, and this will be R sin theta. So now obviously, when we walk, we don't move upwards, like we don't fly when we walk, and that is mainly the component which is responsible for walking is R cos theta. That enables us to move forward walking. Let us move on to the last very interesting topic of laws of motion, and that is the horse cart problem. So let us draw a cart here. This is, let us say this point represents the horse. Let us say, and this is a string, we can say, which connects this cart to this horse. So again, this is the horse foot. So as we saw in the last case, the case of walking, the force applied is in this direction. The normal reaction is in this direction. This is theta. This is R cos theta. This is R sin theta. R r sine theta, and this is let's say the horse is of mass m, and this is mg. Mg is the force, again it is the force of gravity which is applied by the earth on the horse's foot. The string, there is a force tension T, which is tension is a force which can be found in strings, and it is always away from the point. So it is away from this point, it is away from this point. Tension T, tension T. This is a cart, let's say it is of mass capital M, again a force capital Mg, again it's the force of gravity exerted by the earth on this cart, and another force, let's say this is the normal reaction, R dash we can say. Let's say this is it is not frictionless, there is friction also, which opposes, friction is a force which opposes the motion of the system, we can say in this case, of the body. So it opposes the motion of the cart and the horse, so it acts, basically they want to go towards this side of, so friction will act opposite to this side, opposing the motion of the system. So now we can see from here that r sine theta, which is this force, it is equal to small mg. So now for the horse, r sine theta is equal to small mg, and so for the horse to move forward, we actually, basically these forces and these two forces, they cancel each other out because they are equal. So r is equal to F and r sine theta is equal to mg. But if r cos theta and tension also become, tension T, this force, they also become equal, then the horse will not move only. So for the horse to move in this direction, this force has to be greater than this force. So that means r cos theta minus tension T is equal to mass into acceleration. This is the net force. This is the net force. So again, F is equal to ma. Net force is equal to the mass of the horse into the acceleration of the horse. And now for the, this is because basically the cart will move if r cos theta is greater than tension T. Tension T right here. Now for the cart to move, I'll write it here. And this is equation 1. Now for the cart, r dash is equal to capital Mg. R dash is equal to capital Mg. These two forces cancel each other out. And for the cart to move, tension T, this tension T has to be greater than the friction which is opposing the motion of the system. So that means tension T minus friction F is equal to, this is the net force. Net force is equal to mass, capital M, into acceleration. Acceleration of the body will remain the same. The acceleration of the cart is equal to the acceleration of the horse. So they are represented by the same letter A. And this is, let's say, equation 2. Now we want to get rid of tension because we don't want it in our final equation. So we can see that if we add these two equations, we can eliminate T minus T plus T will get eliminated. So now adding 1 and 2, we get r cos theta minus T plus T will get cancelled. R cos theta minus F, which is the friction, is equal to small ma plus capital Ma. From here we can take A as common, so we will get A is equal to r cos theta minus F upon, this is small m plus capital M. So this will be this right here is our final equation. It's our final answer which explains the acceleration of the horse and the cart, which will remain the same. And yeah, so this is the equation, and that is it for laws of motion. I hope you guys enjoyed this video. I've explained almost everything possible with all my knowledge. And please like, share, comment, subscribe, and I'll see you again in the next video. Thank you so much and have a nice day.